Floating photoactivated catalyst microspheres, Richard Holditch and Gilbert Sharma, Department of Chemical Engineering, Loughborough University. The Technology Strategy Board has produced a report, Nanoscale Technologies, covering the period 2009 and 2012. In the report, Table 4 has the market revenue in 2007 and the potential revenue in 2015, broken down into sub-area. The sub-area of interest to this project is nanoparticles contained within the water and environment area. The projected nanoparticles 2015 revenue being $2 billion. Our particular challenge and opportunity is making and using floating catalyst microspheres activated by UV light for water treatment. This would enable the in-situ destruction of pollutants. There would be no need for adsorbents to be taken offline and regenerated, so there is less waste, lower energy costs, and consequently a lower carbon footprint. The problem with photocatalysis is that it needs light and ideally air and water together. Particles block the light, they scatter the light, and nanoparticles are effective, but they are too fine. It's difficult to separate them and recycle them. We wish to have a project to be cost effective, both in terms of generating the microspheres containing the nanoparticles for the photocatalysis, and also to facilitate the easy recycle in a cost-effective way of those nanoparticles. An oil droplet, or any drop lighter than water, will naturally float, but obviously it will coalesce. One way of preventing coalescence on a drop is to use a surfactant acting at the interface between the oil drop and water. Particles act as effective surfactants as well, and this is the nub of the technology we're talking about. It's to provide of a particle stabilized vegetable oil drop, and clearly it will float to the surface. If we have other particles on the surface, we now have a raft of floating catalytic microspheres. The ultraviolet light can be provided by artificial sources to enhance the process, and it would also operate with sun if that was required for a really low energy process. So here we now have our light, air and water all combined together for our photocatalytic process. Just move that down and out the way, and what happens is that free radicals are formed on the surface of the floating photocatalytic particles, and these free radicals are very effective at destroying any organics in their vicinity. So endocrine disrupting compounds, herbicides, atrazine, pesticides, all those materials would be destroyed at the surface of the water. This demonstrates the ability of producing such droplets. It's a membrane emulsification process, and very uniform drops are being produced of a vegetable oil in water. This is stabilized by a surfactant rather than particles. If we had titanium dioxide particles here to stabilize the drops, you wouldn't be able to see anything, it would scatter the light. So this is an illustration of membrane emulsification using a surfactant rather than particles to stabilize the drops. But the principle is the same. We have generated these floating photocatalytic particles. Here they are. It's a nanocomposite because the shell surrounding the vegetable oil drop contains the catalyst, the titanium dioxide. And clearly you can see below the floating particles clear water. These are easily separated particles from the water. They easily float, and we have applied for a patent for this technology. This demonstrates the utility of the floating catalytic particles. Here we have blue-dyed water before activation with UV. We can still see the rafts of floating catalytic particles here. And this is the same dish later. It's on a darker background because the blue dye's gone. It has been destroyed by the floating catalytic particles. The particles are still there, still floating on the surface. They're not degraded in the process themselves. Being floating particles, they are easy to separate and can be recycled for putting through the UV contactor. And we have some designs which enable highly efficient UV contacting using the floating principle again. So that's something that we also wish to do as part of the project, to look at contactor design and recycle. It's worth pointing out that the inner core of these drops is not simply just vegetable oil, but it is possible to provide a foamed mixture using air. So a substantial part of the inner core is in fact air, to enhance the buoyancy, to enhance the floating nature of the particles, and to reduce the amount of vegetable oil or other lipid required to create the floating particles. So on the outer surface here, marked in red, we have the titanium dioxide or other nanoparticle for floating photocatalytic use, and the inner surface is a lipid, can be a solid lipid rather than a liquid lipid, and a substantial amount of air to also enhance the floating capability. So producing these particles is simple by membrane emulsification. It's also very cheap. There is no waste generated in the process of making the microspheres. The nanoparticles stabilize the drops and can be used again and again. The only way out of the system for the nanoparticles is on the surface of the drops, the composite particles. Using this technology, we can control the microsphere size easily using membrane emulsification processes. Higher shear gives smaller microspheres, for example. It provides a very low density nanoparticle composite where the nanoparticles are around the edge where they are effective, and the whole process, if we do a calculation based on mass transfer resistance, the whole process is an extremely cheap way of treating water for removing some of the compounds mentioned previously. So cost-effective microspheres. I say there's no waste. Here is a membrane that's used in the membrane emulsification process. It's not a solid can, it's a perforated can, perforated hole, perforations there for the membrane emulsification process. That is a small version of a canister that can be mounted inside this vessel here. This was designed and built for 300 kilograms per hour production of particles, different particles to the floating ones, different project, but nevertheless it's possible to achieve that throughput of particles using this membrane emulsification process. So it's a cheap, robust way of making particles. What we're looking for are partners to help with this application demonstrator. We need to test real waters rather than the laboratory simulated waters. We need to also test the products that are being formed during the process. We need to consider other particles that could be present, such as colloids, and that may require pre-filtration, or it may not. We may be able to simply modify the microspheres to accommodate the presence of other colloidal material. And primarily we need to also work on ensuring the microspheres are easily recycled into the process for further use. So it's a Loughborough University project, but we are seeking commercial partners to enable us to achieve intentions for the test water. Obviously we would like to advice and collaboration in this technology strategy board project, and ideally a collaboration with several end users as well as technology suppliers. We're thinking of putting together a consortium of interested parties who may wish to help us with this technology strategy board proposal and have a direct input into it with a view to commercialising the outputs, the results from the project. If you are at all interested in helping us with this project, then please do contact either myself, Richard Holditch at Loughborough University, or my colleague Gilbert Sharma at the same place. Our emails addresses are here. We hope to hear from you. We welcome all comments. Thank you.